In this video, we are going to show you how to write the electron configurations for the atoms on a periodic table. So let's start with a few definitions. First of all, electron configuration is a description of the orbitals, of which orbitals are occupied by electrons. Now, it's very important to understand the electron configuration for a particular atom because how the electrons are configured in an atom give that atom its physical and chemical properties. So for example, the noble gases are very unreactive. They don't react with other atoms in chemical reactions. That's because of their electron configuration. If you take a group 1 atom or a group 1 element, sodium, potassium, if you take some of that metal and you were to put it in water, it reacts very violently in water and gives off smoke and fire and sparks. And again, it reacts that way because of its electron configurations. And so, as we'll see later, when we begin to look at the chemical properties of atoms, what types of ions they form, it's all related to their electron configuration. So it's very, very critical that we have a good understanding of how to write the electron configurations for atoms, and then we begin to understand what these configurations mean. A couple of more definitions. Degenerate orbitals is a term we use, and those are orbitals that have the same energy. So for example, in the second shell, there are 3 p orbitals. Those 3 p orbitals all have the same energy, so we say those are degenerate. In the n equals 3 shell, we have d orbitals. There are 5 d orbitals. Now those d orbitals, like the p orbitals, they're located spatially different along the x, y, and z axis, but they all have the same energy. So an electron in one d orbital has the same energy as an electron in a different d orbital. So again, those 5 d orbitals are degenerate to each other. And then what we're going to be discussing in this video are what are called ground state electron configurations. That's the lowest energy electron configuration. It's possible for electrons to gain energy and jump up to higher orbitals, and that's called excited state. And we'll look at that later, but right now we want to write the most stable electron configuration possible for an element, and that is what we call the ground state electron configuration. Now when we are writing electron configurations for any element, we must follow a few different rules. There are 3 of them that we want to be aware of. There's what's called the Aufbau Principle. Aufbau meaning building up, and that tells us that electrons occupy the position of lowest energy. So an electron will go into, when it goes into an atom, it will go into the lowest energy position possible. Generally the one closest to the nucleus is the lowest energy. So it wants to go in the lowest energy orbital. So we need to keep that in mind when we're filling these electron configurations. Next is Hund's Rule. Electrons in the same subshell occupy empty orbitals rather than pair up. We'll demonstrate that for you in just a minute. But again, the second shell, we have p orbitals. There are 3 p orbitals. The electrons will go into, if you have 3 electrons, 1 electron will go into each of the p orbitals before they begin to pair up. Again, that's a lower energy configuration. The electrons want to spread out as far as possible. So we'll demonstrate that for you in just a minute. And then the third rule we need to keep in mind is the Pauli exclusion principle. No 2 electrons in an atom have the same 4 quantum numbers. What that means is that if you have 2 electrons in the same shell, in the same orbital, the electrons must have different spins. And that's defined by the m sub s, or the magnetic spin quantum number. So one electron will have a +1/2 and have a clockwise spin. The other will have a -1/2 and have a counterclockwise. Again, which electron has which spin is irrelevant. We just need to appreciate that they do have opposite spins when two electrons are in the same orbital in the same shell. So let's practice writing a few electron configurations. And we're going to write electron configurations. We're going to show them in two different ways. We're going to write what's called an arrow notation, where we express each electron as an up or down arrow. Then we're going to write the standard electron configuration. So we'll show you both of those. So let's practice several of these to give you an idea of how these are done. So why don't we start with the simplest element, which is hydrogen. Neutral hydrogen has one proton and one electron. When we write electron configurations, we must follow our rules, the first of which is the Aufbau Principle. The Aufbau Principle tells us that when electrons are added to an atom, or the electrons are going to go into the lowest energy shell and the lowest energy orbital in that shell. Electrons want to be as close to the nucleus and therefore have the lowest energy possible. So the lowest energy shell is the first shell, and the first shell has only one orbital in that, and that is an s orbital. Okay? And so to represent the hydrogen's one electron, we will draw an arrow. It could be either an up or down arrow, it doesn't matter. So this would represent hydrogen's one electron, and it is in the 1s orbital. We could also express this like this. We could say 1s, the 1 representing the n number, the first shell. The L value is represented here with an S-shaped orbital. And hydrogen has one electron, so we'll put the number 1 here. So both of these, the arrow notation or the regular electron configuration, are correct ways of writing the hydrogen electron configuration. Which you would have to do would be specified in the particular problem. You would of course be told to either write the electron configuration of an atom using the arrow notation or just the standard notation. And that's what I'll call this, the standard notation. Okay? Let's try our next atom on the periodic table is helium. Okay? Helium has 2 electrons, and the first electron is going to go in the lowest energy orbital in the lowest energy shell. So it's always going to start with the 1s. Helium has 2 electrons, and quantum mechanical model of an atom tells us that each orbital can hold a maximum of 2 electrons. So helium's second electron will also go into the first shell. Okay? And these 2 electrons must have opposite spins. Electrons in the same orbital must have opposite spins. That's the Pauli exclusion principle. So this represents their m sub s, the magnetic spin quantum number, tells us that one of these has a plus 1/2, the other has a negative 1/2. Again, which is which doesn't matter. We're just concerned that they have different spins. So for helium, we could write its electron configuration as 1s2. Again, 2 electrons in the first shell in the s orbital. So let's try a different atom. Let's go with a slightly larger, lithium. Okay. Lithium has 3 electrons. The first one's going into the 1s, and the second one will also go in the 1s with an opposite spin. The third one will have to go into a new shell. It will go into the n equals 2 shell, and the lowest energy orbital in the n equals 2 shell is the 2s orbital. And so we'll put that electron here. Again, either up or down spin, it doesn't matter. And we could represent lithium's electron configuration also as a 1s2, 2s1. Let's try one that is slightly larger. Let's go with nitrogen. Okay? So let's try the electron configuration for nitrogen. Nitrogen has 7 electrons. The first 2 electrons will go into the lowest energy shell and orbital, the 1s. The next 2 electrons will go into the 2s. Okay? So we have 4 electrons placed. We have 3 more. Okay? The n equals 2 shell contains s orbitals, and it also contains p orbitals. There are 3 p orbitals. Again, we have one along the x-axis, one along the y-axis, and one along the z-axis. Which doesn't really matter here because they're all the same energy. All 3 of these p orbitals have the same energy, and so we call those degenerate orbitals. Okay? So nitrogen has 3 more electrons. We're going to put one here, one here, and one here. We put them each electron in we half fill each of these degenerate orbitals, and that follows Hund's rule. Hund's rule tells us that electrons want to have the lowest energy possible, and to do that, they will first each one will go into an individual degenerate orbital, and then if we have more, we'll go back and start doubling up. Also, each of these electrons in these p orbitals, the first, that when they're half filled, all of these electrons must have the same spin. So all of these must either be up arrows or down arrows. So this would be the electron configuration for nitrogen in the arrow notation. To write it in the standard way, we could put 1s2, 2s2, and then 2p, we would put 2p3. Okay? Now remember, where these orbitals, how do you know that there are s and p orbitals in the n equals 2 shell? What we're doing here is we're applying what we learned when we were when we learned about quantum numbers. Remember, you have n values, you have L values, and you have m sub L values. Okay, you also have m sub S values, but let's just look at these. If you have an n of 1, that means we're talking about the first shell. The n equals 1 has an L value of 0. An L value of 0 has an m sub L value of 0. So if you're not clear on how we got this, again, review the quantum numbers in your video and in your text. And remember, the L subshell, that tells us that we have S-shaped orbitals. So an L of 0 indicates an S-shaped orbitals in that subshell. The m sub L tells us that there is only one orbital of the S type. Remember, if you have an n of 2, now we're talking about the second shell. The L values are 0 and 1. The m sub L values for an L of 0 are 0. The m sub L values for an L of 1 are -1, 0, and +1. So again, what do these tell us? That means the second shell, n of 2, we have one S-shaped orbital, and we have 1, 2, 3 P-shaped orbital. An L of 1 tells us that the orbitals in that subshell are P-shaped. This tells us how many we have. So the second shell has one S orbital and 3 P-shaped orbitals. Okay? But that's all it contains. So any more electrons, if we filled up the p orbitals, then we'd have to go to the next shell, the n equals 3 shell. So be comfortable again with the quantum numbers and be able to apply those when you're writing electron configurations. Why don't we try one more here? Let's try sodium. Sodium has 11 electrons, and so let's draw the arrow notation for sodium. We're going to start with the 1s. We're going to put 2 electrons in there. We're going to the next highest, that's a 2s, the next highest energy orbital in the second shell. We're going to put 2 electrons there. They must have opposite spins. Okay. Sodium, we still have some more electrons we haven't accounted for. So sodium, we have 4 accounted for. Sodium has 11. Okay, so we still have 7 more to place. We're going to put 1 here, 1 here, 1 here. Again, we're following Hund's rule. each of these electrons in its own degenerate orbital with the same spin. Now we go through and we start doubling up, and they must have opposite spins, okay, representing the m sub s, or magnetic spin quantum number, plus 1/2, negative 1/2, again, which is which, doesn't matter. So we've placed 2, 4, 6, 8, 10 electrons. We have one more to place. Our second shell has no more orbitals in it, so we must start a new shell, the 3s, and we're going to put one electron in the 3s. So this is the arrow notation for sodium. We could write that in a more standard way of 1s2, 2s2, 2p6, 3s1.